Fast-moving object the size of Manhattan is hurtling towards our solar system. Comet, asteroid, or something else. Astrophysicist believes there's a strong likelihood this is a craft of alien origin.
NASA's Deep Space Monitoring Network has rarely been as tense as it is now. 7 newly identified comets, including the already notorious 3 I/Atlas, are diving into the inner solar system on trajectories that place them under intense scientific and security watch. For decades, comets were largely seen as distant wanderers that passed by the sun, briefly displaying tails of gas and dust before retreating back to the outer solar system. But the recent wave of comet discoveries arriving in near-Earth space together, led by 3 I/Atlas, has triggered a level of attention that few events in planetary science can match. This convergence of icy bodies from the outer reaches of the solar system is not just a moment of spectacle. It is a collision of astronomy, physics, and the potential hazards posed to Earth by these cosmic visitors. Before we start, smash the like and subscribe buttons for more updates. The centerpiece of this heightened alert is 3 I/Atlas, a comet that first startled astronomers by being classified as an interstellar object. It joined a tiny club of bodies alongside 1I Oumuamua that did not originate in our solar system but instead crossed the gulf of interstellar space. Its path, speed, and composition already made it extraordinary. Now, its sudden companionship with 6 other comets diving sunward has created an entirely different challenge. Each of these 7 comets is unique, yet together they form a collective event that can test not only the observational power of NASA's instruments, but also the limits of our understanding about how such groups of objects can appear almost simultaneously. The arrival of multiple comets at once is not without precedent, but it is exceedingly rare. Usually, a single long-period comet captures the imagination of the public and the attention of scientists. The 7 currently on course through the inner solar system create overlapping observational windows, making it difficult for astronomers to decide how best to allocate telescope time. Priorities must be set, data pipelines must be expanded, and coordination across observatories on Earth and in space becomes critical. NASA's Planetary Defense Coordination Office, designed to monitor and assess threats from near-Earth objects, has had to expand its scope from asteroids to an unexpected flood of comets. This demonstrates the flexibility of the network, but also underscores the importance of planning for scenarios that once seemed improbable. What makes the situation more complex is that comets are notoriously unpredictable. Their outgassing, the process of sublimating ice-releasing gas and dust as they heat up near the sun, can dramatically alter their brightness, behavior, and even trajectory. A comet's apparent size in the sky can suddenly grow, or its nucleus can fragment into multiple pieces, creating swarms of smaller bodies that pose their own risks. When there are 7 such objects in close succession, the statistical likelihood of at least one behaving in unexpected ways increases. For scientists, this unpredictability is a gift of natural experimentation. For engineers and those responsible for planetary defense, it is a variable that must be constantly recalculated. The story of 3 I/Atlas itself already bends the imagination. Being of interstellar origin, it carries chemical fingerprints from beyond our solar system. Its ices and dust grains are not the result of the same planetary nursery that formed Earth, Jupiter, or Saturn, but rather of a star system light years away. When NASA trains its instruments on 3 I/Atlas, it is not just watching a comet, it is reading a page from another cosmic history. In the laboratory, meteorites have occasionally carried hints of interstellar grains, but here the entire object is alien in origin. Now, as this body is accompanied by 6 comets of solar system origin, there is an extraordinary chance to compare alien chemistry against the homegrown building blocks of our own celestial backyard. This parallel arrival of comets also presents an opportunity to refine models of solar system dynamics. Long-period comets often hail from the Oort cloud, a vast spherical shell of icy objects thought to surround the sun at immense distances. Perturbations from passing stars, galactic tides, or giant molecular clouds can dislodge these objects, sending them hurtling inward. But the simultaneous arrival of multiple bodies suggests there may be clustering mechanisms at work, perhaps triggered by a common disturbance. Astronomers have speculated about these triggers for decades, Yet events like this provide the rare data needed to test such ideas. Could a distant stellar passage have nudged a small group of Oort cloud bodies toward the Sun together? Or is there a resonance in orbital mechanics that shepherds comets into similar paths over time? These are no longer abstract speculations, but pressing questions driven by real trajectories. Beyond scientific curiosity, the reality of 7 comets diving toward the Sun raises broader implications about planetary safety. Even though most comets pose no direct risk of impact, their presence creates a dynamic sky filled with variables. The trails they leave behind, composed of dust and debris, can intersect Earth's orbit months or years later, producing meteor showers or, in rare cases, meteoroid hazards. Every comet observed in detail enriches our database for understanding these risks. In the long run, these data may influence how humanity prepares for a future in which a comet, not an asteroid, becomes the object requiring deflection or mitigation. Unlike most asteroids, comets arrive with less warning, often emerging from the outer solar system on highly eccentric orbits that give observers little time to react. The clustering of 7 together is a rehearsal in some sense for scenarios where readiness and speed of response could determine outcomes. NASA's array of instruments is being tested to its limits by this multi-comet event. Space-based observatories, such as the Hubble Space Telescope and the James Webb Space Telescope, offer unparalleled ability to analyze the composition of cometary ices and gases. Infrared observations from Webb can detect the faintest heat signatures, revealing the hidden chemistry driving comet activity. At the same time, ground-based telescopes like those at Mauna Kea, Palomar, and the Atacama Desert are monitoring the evolving brightness and morphology of these objects. Coordinating these efforts across time zones and hemispheres requires an international network of astronomers and agencies, highlighting the inherently global nature of watching the skies. For the public, the prospect of 7 comets passing near the Sun in quick succession has a poetic allure. Comets have always occupied a liminal space in human culture, half omen and half marvel. From ancient chroniclers who saw them as harbingers of change to modern skywatchers who marvel at their beauty, comets stir a unique mixture of awe and apprehension. This new gathering of cosmic wanderers continues that tradition, but with the added weight of modern science. The narratives of doom have been replaced by meticulous calculations of orbital dynamics, yet the sense of watching forces larger than ourselves remains intact. When a cluster of comets sweeps through the inner solar system, even the most skeptical observer can feel the pull of cosmic perspective. The presence of 3 I/Atlas among the 7 adds a distinctly interstellar dimension. Its hyperbolic path ensures that, unlike the others, it will not return after its perihelion passage. This is a once-only chance to study it. Scientists hope to squeeze every bit of data possible from this brief visit, analyzing isotopes, dust composition, and outgassing behavior. Each fragment of information enriches our understanding of how planetary systems elsewhere may form and evolve. Comparing these findings to the 6 other comets provides a control group, a kind of cosmic experiment designed by nature. Do interstellar comets carry different ratios of water isotopes? Do they release gases that are rare or absent in solar system comets? These are not just academic questions. They touch on the universality of chemistry and the potential for life elsewhere. The logistics of studying 7 comets also underline the limits of current infrastructure. Observatories cannot be everywhere at once, and data bandwidth is finite. Researchers must decide whether to focus deeply on 1 or 2 comets or to spread attention thinly across all 7. The arrival of 3 I/Atlas tips the balance as its uniqueness demands priority. Yet ignoring the other 6 would squander an unprecedented comparative opportunity. These decisions involve more than science. They involve politics, funding, and international cooperation. Who gets access to telescope time? Which research proposals take precedence? Behind the spectacle in the sky is a complex choreography of human institutions trying to keep pace with celestial timing. Meanwhile, the physical realities of comets ensure that surprises are inevitable. A nucleus could split suddenly, as has happened with past comets producing secondary objects. Jets of gas could push a comet onto a slightly altered path, challenging predictions. Dust tails could expand in unexpected ways, crossing paths with spacecraft, or even contributing to auroral activity on Earth if particles interact with our magnetosphere. In every case, the lesson is the same. Comets cannot be fully domesticated by equations. They carry the unpredictability of volatile ices and primordial dust, sculpted by forces beyond simple calculation. This is part of their danger, but also part of their charm. The role of amateur astronomers in this unfolding drama should not be underestimated. Around the world, thousands of skywatchers with modest telescopes and cameras contribute observations that supplement NASA's professional data. Their vigilance often detects sudden outbursts or brightness changes before large observatories can respond. In a sky crowded with 7 comets, these contributions become even more valuable, ensuring that no sudden development goes unnoticed. This partnership between professionals and amateurs echoes the deep tradition of astronomy as a field where passion and precision converge. As the comets draw closer to the sun, their tails will lengthen and their displays may even become visible to the naked eye from Earth. Such an occurrence would transform a scientific watch into a cultural event. History shows that great comets ignite the public imagination, inspiring art, literature, and sometimes even shifts in worldview. If several comets become simultaneously visible, it could create a spectacle unmatched in living memory. For NASA, this represents both a challenge and an opportunity. A challenge to keep public communication accurate and grounded, and an opportunity to engage a global audience with the beauty and importance of planetary science. The larger implications extend far beyond the immediate spectacle. These comets are messengers from the edges of cosmic geography, carrying samples of the raw material from which planets form. Studying them informs models of planetary formation, not just in our solar system but throughout the galaxy. They are time capsules preserving chemistry from billions of years ago. Every spectrum taken, every image captured, is data that enriches our sense of where we came from and how unique or common our planetary system might be. The sudden congregation of 7 comets underscores how much of the universe remains untamed and unplanned, arriving without warning to challenge and enlighten us. For NASA, being on alert is not a state of fear but of readiness. The 7 comets diving inward demand vigilance, coordination, and imagination. They demand that we test our instruments, refine our models, and expand our thinking. They remind us that the sky is not static but alive with motion, chance, and discovery. And they reinforce a truth that astronomers have always known. The universe does not operate on our schedule. It brings its wonders and its challenges when it chooses, and we must be prepared to meet them with both caution and curiosity. The watchfulness surrounding the 7 comets, including the enigmatic 3 I/Atlas, has not only stretched scientific schedules but also propelled new theoretical considerations. Each fresh discovery forces a reassessment of long-held assumptions about the mechanics of comet influxes and the architectures of distant reservoirs of ice. With so many objects entering the inner solar system in a compressed time frame, astronomers are beginning to question whether the interplay of galactic influences on our solar system has been underestimated. It is possible that the gravitational tides of the Milky Way itself, imperceptible on short timescales, are slowly nudging clusters of icy bodies from the Oort cloud and sending them inwards. Events such as this compel researchers to examine how our solar system is interconnected with the larger galaxy that cradles it. The gravitational choreography of these 7 comets is nothing short of mesmerizing. Each one carries its own orbital eccentricity, inclination, and perihelion distance, yet they weave together like threads of an interstellar tapestry. Their paths reflect subtle perturbations from the giant planets, especially Jupiter, whose immense mass often acts as both gatekeeper and disruptor. A close encounter with Jupiter can fling a comet outward into the abyss, or send it plunging sunward at increased velocity. With 7 bodies diving inward at once, the likelihood of intricate gravitational interactions increases dramatically. This presents an unparalleled chance to refine simulations of comet dynamics, allowing researchers to cross-check predictions with real-time behavior. These interactions highlight the solar system as a living laboratory, one in which planetary giants and icy wanderers engage in an eternal exchange of momentum. The very diversity of these comets adds richness to the unfolding narrative. Some of them are believed to originate from the Oort cloud, while others may come from the scattered disk beyond Neptune. Their nuclei vary in size, from small icy kernels only a few hundred meters across to larger behemoths spanning several kilometers. This variation is vital for understanding the evolution of icy bodies over billions of years. Smaller comets often disintegrate more rapidly under the heat of the sun, while larger ones can survive multiple perihelion passages, leaving longer observational trails. By monitoring 7 distinct bodies nearly simultaneously, NASA and collaborating institutions can collect a comparative data set that would otherwise take decades to assemble. It is as if nature has decided to compress centuries of cometary evolution into a single chapter for humanity to read. The visual displays expected from this group of comets will also become natural experiments in how solar radiation interacts with volatile materials. As these icy bodies approach the sun, solar photons penetrate the crust of the comet, releasing gas from hidden reservoirs. Dust carried along with the gas forms vast tails stretching millions of kilometers through space. By analyzing the brightness, structure, and evolution of these tails, scientists can measure the relative abundances of water, carbon dioxide, methane, ammonia, and other volatiles. Each tail is not merely a spectacle, but a diagnostic tool, a beacon carrying information about the primordial chemistry that shaped planetary bodies. With 7 such beacons shining nearly at once, the observational window expands into a panoramic survey of cosmic composition. Another aspect that demands attention is the thermal stress exerted on cometary surfaces. When approaching the sun, a nucleus undergoes violent changes in temperature, often leading to cracking, shedding, and explosive outbursts. These processes can suddenly expose pristine material from the comet's deep interior, untouched since its formation. Catching these outbursts in action is exceedingly rare, but with 7 comets arriving in close succession, the odds of witnessing such events improve considerably. For planetary scientists, this is akin to drilling into the untouched strata of Earth's crust, except the drilling is done by sunlight and the results are visible across the void of space. The comparative approach becomes especially intriguing when considering 3I/Atlas, whose interstellar origins sets it apart. Its behavior near the sun may not align with patterns established by comets born of our solar system. For instance, the volatile compounds it releases could include exotic species uncommon in local comets, or its dust-to-gas ratio might defy expectations. Such anomalies would suggest that planetary nurseries across the galaxy operate under varied conditions, producing comets with distinct signatures. If, on the other hand, 3I/Atlas closely resembles its solar-born companions, it would hint at a surprising universality of cometary chemistry. Either outcome advances understanding of planetary formation as a cosmic process rather than a purely local phenomenon. The flurry of activity has also rekindled discussions about the role of comets in delivering ingredients for life. For decades, scientists have speculated that Earth's water and perhaps even organic molecules essential to biology were delivered by impacts from comets in the early days of the solar system. The detection of amino acids and complex organics in cometary material supports this hypothesis. The simultaneous study of multiple comets offers a rare chance to probe whether such organic molecules are ubiquitous or rare. If several of the current 7 show signs of amino acids, hydrocarbons, or nucleobase precursors, it strengthens the idea that life's raw materials are not just common but practically inevitable wherever comets roam. Equally significant is the question of habitability on other worlds. Mars, Europa, and Enceladus have all been considered as possible havens for microbial life. Yet their supply of water and organic matter remains a subject of debate. Understanding cometary delivery systems sheds light on how often such resources may have reached these bodies in the past. The 7 comets now under observation act as analogs for past delivery events, their present behavior shedding light on ancient bombardments that shape the habitability of diverse environments across the solar system. Watching them closely could inform the future search for life beyond Earth. The sheer scale of coordination required to track 7 comets also demonstrates the global nature of astronomy. No single nation or institution can cover all the observations necessary. Networks of telescopes spread across continents and spacecraft positioned across the solar system must pool their resources. Instruments like the Solar and Heliospheric Observatory SOHO and the Parker Solar Probe may capture near-Sun interactions, while infrared arrays and spectrographs on Earth detect subtle signatures of gas release. Even planetary missions orbiting Mars or stationed at Lagrange points may provide valuable perspectives. This blending of efforts highlights the interconnectedness of modern science, where shared data becomes the currency of discovery. Such collaboration extends beyond professional circles. Citizen science platforms now allow amateurs to upload images, light curves, and spectra in near real time. These contributions can help refine orbital models or detect sudden changes in brightness. The excitement generated by 7 comets ensures a wave of participation from enthusiasts worldwide, creating a moment where the line between professional and amateur blurs. Every observer, from the most advanced spectrograph to the simplest backyard telescope, becomes part of a planetary-scale effort to decode the stories carried by these icy wanderers. The unpredictability of comets ensures that surprises lie ahead. One of the 7 may disintegrate entirely, scattering debris across space in a cloud that changes the character of meteor showers years down the line. Another may brighten unexpectedly, briefly becoming a celestial marvel visible to millions without aid. Each development alters the narrative, shifting scientific focus and public fascination. The volatility of comets is precisely what makes them compelling. They resist prediction, forcing scientists to balance theoretical models with real-time adaptation. The gravitational environment of the solar system ensures that the journeys of these comets may not end after this perihelion passage. Several may return in centuries or millennia, transformed by their solar encounters. Their surfaces will be scarred by sublimation, their orbits reshaped by gravitational nudges. In this sense, observing them now provides a baseline for long-term evolution. Should they be seen again in the distant future, comparisons with today's data will tell stories of survival, change, and decay. For 3I/Atlas, however, this is a farewell performance. It will never return, making every observation uniquely precious. As the 7 comets streak sunward, they also interact with the solar wind, a constant flow of charged particles streaming from the sun. This interaction creates magnetic draping around cometary atmospheres and generates aurora-like emissions detectable in ultraviolet and X-ray wavelengths. With multiple comets active at once, researchers can study how varying sizes and compositions affect these interactions, refining models of plasma physics in environments beyond Earth. The Sun-comet relationship is not just a matter of visual spectacle, but a field experiment in space weather dynamics, relevant to understanding how solar radiation shapes atmospheres across the solar system. The timing of these arrivals, clustered together, may also influence future strategies for planetary defense. Most planning has focused on asteroids, whose orbits are easier to calculate years in advance. Comets, with their long-period orbits and sudden appearances, pose a different challenge. By tracking 7 simultaneously, scientists can stress test detection networks, refine impact probability algorithms, and evaluate how quickly orbital predictions can adapt to sudden changes. These lessons may one day inform real-world scenarios where a comet poses a direct hazard to Earth. The present moment serves as both spectacle and training exercise. Another dimension arises from technological innovation spurred by events like this. As comets grow in importance, new instruments may be proposed or accelerated. Concepts for fast-response spacecraft capable of intercepting a newly discovered comet within years rather than decades gain momentum. Miniaturized probes or CubeSats hitchhiking on larger missions could be designed specifically to rendezvous with cometary nuclei. The urgency of 7 comets arriving at once fuels arguments for preparing such hardware in advance, ensuring humanity can seize opportunities without waiting for the next rare cluster. The educational impact of such an event is profound. Schools, universities, and outreach programs seize the chance to connect students with real-time science. Lessons on orbital mechanics, chemistry, and planetary defense acquire immediacy when 7 comets are visible in the sky or in streamed telescope feeds. The sense of participation in a global event enhances scientific literacy and may inspire the next generation of astronomers and engineers. Beyond classrooms, the sheer beauty of cometary tales ignites cultural imagination, potentially leaving imprints on art, music, and literature as they have for millennia. In contemplating the philosophical weight of 7 comets diving inward, humanity is reminded of its place in the cosmos. These icy bodies predate civilization, predate even the formation of Earth's continents. They represent continuity across billions of years, relics unchanged until their sudden dive toward the sun. To watch them is to confront timescales far beyond human experience, to glimpse a universe in motion where our existence is but a fleeting moment. This awareness enriches not only science but also the human sense of meaning, positioning us as both witnesses and participants in a cosmic story. The scientific implications of this cluster extend into exoplanetary studies as well. Observations of other star systems frequently detect exocomets, inferred through transient dips in stellar light caused by dust tails. By studying the behavior of our local comets in exquisite detail, astronomers build analogs to interpret these distant signals. The 7 comets now under NASA's alert provide a calibration set for exocometary science, allowing a bridge between our neighborhood and the wider galaxy. In this way, local phenomena become universal lessons. As the days and weeks unfold, the story of the 7 comets and 3 I/Atlas in particular will deepen. More precise measurements of trajectories, nuclei sizes, and gas emissions will emerge. Each new data point enriches an already unprecedented situation, yet the true significance may not lie solely in the science, but in the collective awareness fostered by this convergence. Humanity, scattered across continents and cultures, is united in watching icy wanderers from the edge of existence sweep into view. It is a reminder that the sky belongs to all of us, and that its mysteries, however unpredictable, invite us to learn together. The convergence of 7 comets, headlined by the extraordinary interstellar visitor 3 I/Atlas, continues to reshape how astronomers conceptualize both the solar system's architecture and humanity's relationship with cosmic phenomena. As these icy bodies carve their luminous paths toward the sun, new dimensions of exploration open up, extending beyond pure astronomy into disciplines such as geology, climatology, computational science, and even philosophy. Each thread of this event pulls on another, weaving a story of discovery that stretches across both scientific frontiers and human imagination. One of the most fascinating aspects of the 7 comet scenario lies in its geological implications for Earth and other terrestrial worlds. Comets are thought to carry pristine material left over from planetary formation, yet their impacts have historically left indelible marks. The Earth's geological record holds signs of ancient bombardments, when cometary bodies and asteroids delivered immense energy to the surface. While no such direct threat is posed by the current cluster, the study of their composition and behavior deepens understanding of those formative epochs. By analyzing their isotopes and volatile contents, researchers can refine hypotheses about how Earth acquired its water, how its early crust may have been altered, and how life-supporting molecules could have been seeded. Mars, too, with its enigmatic traces of past water, may owe part of its history to similar cometary deliveries. These 7 comets, by revealing their internal makeup, provide living analogs for the building blocks that sculpted planetary landscapes long before humans emerged. From a climatological standpoint, the arrival of multiple comets offers a chance to explore how dust and gases released into space might influence Earth's atmospheric environment. While the quantities involved are usually too small to trigger noticeable changes, there are historical suggestions that large cometary events have coincided with shifts in climate. Dust grains entering the atmosphere can act as condensation nuclei, potentially affecting cloud formation. Some researchers have proposed that spikes in cometary activity could enhance meteor showers, increasing the number of high-altitude meteors that inject metallic ions into the upper atmosphere. Studying 7 comets simultaneously provides a rare laboratory for testing these connections. Even if the present influx does not alter climate, the detailed data gathered will refine predictive models for how cometary debris interacts with Earth's thin protective shell. The computational demands of tracking 7 comets at once represent another layer of challenge and opportunity. Each object's orbit must be modeled continuously, accounting for gravitational perturbations, non-gravitational forces from outgassing, and solar radiation pressure. This requires immense processing power, with supercomputers running simulations that must be constantly updated as new observations come in. The event thus acts as a stress test for computational astrophysics, pushing algorithms to handle complexity and unpredictability at new levels. Lessons learned from this real-time challenge will inform future approaches not only for comet tracking, but also for modeling complex systems such as planetary atmospheres, stellar dynamics, and galactic evolution. The 7-comet influx becomes, in effect, a proving ground for the next generation of scientific computing. Equally captivating is the intersection of this astronomical event with the philosophy of science. For centuries, comets were objects of dread, interpreted as omens by civilizations that lacked the tools to understand their nature. Even after scientific revolutions redefined them as icy remnants of planetary formation, their unpredictability kept them on the boundary between mystery and knowledge. Now, the arrival of 7 at once forces reflection on the limits of prediction and control. It reminds humanity that the universe is not entirely subject to scheduling or planning. In a world increasingly dominated by precise technological systems, the sight of multiple comets blazing across the sky is a reminder of forces beyond human control. It invites humility and re-engagement with the cosmos as something larger than any society or generation. The educational value of such a convergence cannot be overstated. For students at every level, this becomes a real-time case study linking textbook concepts to observable reality. Teachers can guide learners through calculating orbital elements, predicting visibility, or analyzing the chemistry of cometary tails. University researchers can build theses and dissertations around the wealth of new data being generated. Science museums and planetariums can host live events, projecting images from space telescopes and ground observatories to captivated audiences. Each comet, with its glowing coma and sweeping tail, becomes a bridge between professional science and public curiosity. 7 at once multiplies that bridge, creating a festival of cosmic learning. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on 7 comets diving toward the sun? We want to hear from you. Thank you for watching and see you next time.